Hello, everyone. I'm Esther Hanna, Assistant Professor, Department of Information Technology, Women's Christian College, Chennai. In this video, we're going to learn an important concept of operating systems, namely deadlocks. Let's see what deadlocks are. The definition of deadlocks goes like this. It could be defined as a set of blocked process, each holding on to a resource and still waiting to acquire another resource that is held by another process. A process is deadlocked if it's waiting for an event that will never happen. Usually, it requires more than one process to be involved in a deadlocked condition. In such cases, a process is indefinitely postponed and delayed repeatedly over a long period of time, while some other process is given attention and provided with the resource that it needs. Hence, the deadlock problem is a situation that occurs in operating system when any process enters a waiting state because another waiting process is holding on to the demanded resource. For example, let's assume that a system has got two tape drives and these are two resources. There are two processes, P1 and P2, and each require two tape drives to complete their execution. But each one is holding on to one and still waiting for the other one, which would never happen. And this condition can be typically viewed as a deadlocked condition. A deadlock is a common problem in multiprocessing environments where several processes share a specific type of mutually exclusive resources. Another example could be assuming a bridge where a part of the bridge is narrowed, where only one vehicle could move. Hence, traffic can move in only one direction. This could be a deadlock situation where one of the vehicles should back up and give room for the other to move on. Otherwise, the situation will indefinitely be the same. And in course of time, in operating system terms, it leads to a state called starvation, where a process is never given a chance to complete its execution by providing the needed resources. So what is a resource? A resource, it could be any commodity which is required by a process to execute. And it could be of two different types. It could be serially reusable resources or consumable resources. Reusable resources are those that can be reused by another process. Similar, it could be such as the memory space, the I/O devices, the CPU cycles, and so on. Whereas consumable resources are those once produced by a process, it is consumed by another process and never reused. It could be messages sent from one process to another, or it could be interrupts. And in such cases, these resources do not exist after it has been consumed or taken by the other process. So in the system model, we can consider having resources of various types, R1, R2, up to Rn. And each resource can have n number of instances. For example, we were discussing about the tape drives. If there are two tape drives, then that is assumed to be two instances of the tape drive, which is a resource, a type of the resource. So there could be tape drives, there could be printers. These are all different types of resources that a process makes use of during its execution. For a deadlock condition to occur, there are four important conditions that has to simultaneously hold good. These conditions are also called as Kaufman conditions, and which are very, very important ones and called the necessary and sufficient conditions for deadlocks. Number one is mutual exclusion. Number two is hold and wait. Number three is no preemption. and number 4 is circular weights. So what is mutual exclusion? Mutual exclusion property ensures that only one process can make use of a resource at a given time. That means simultaneously no two processes can access the same shared resource. The second condition, hold and wait. This is a property where processes hold on to resources which are already allocated to them and still wait for other resources which are held by other processes. The no preemption property says whenever resources are allocated to a process, it will not be voluntarily taken away from them unless it will not be forcefully taken from them unless they are voluntarily released. So, in a no preemption state, when a process is given a resource, the system waits for the process to voluntarily release the resource that is allocated and does not forcefully take it away from that process. So the circular weight property says it can be viewed as a chain of processes where every process waits for the resource that is held by the next process, still holding on to a resource that the previous one needs. So the chain goes on. So this can be viewed by this diagram. There are two figures here, figure A and figure B. In the figure A, you can see there are two resources and two processes. Process 1 is holding on to resource 1 and still waiting for resource 2. Whereas process 2 is holding on to resource 2 and still waiting for resource 1. And this condition will never complete since every process is waiting for another process which is held by another, waiting for another resource that is held by another process. So on the right side, in figure B, we can see USB is a resource. And there are 3 processes waiting for the USB that is held by another process and still waiting for another USB. So if you look at process 1 is holding on to USB 3 and is waiting for another USB, which is USB 2, which is held by process 2. So a very good method for identifying, a simple method for identifying this condition of deadlocks, which we are discussing, can be done using a graph called resource allocation graph. Once you understood what a resource are, now we'll see how to draw this resource allocation graph. It is a directed graph and consists of a set of vertices and a set of edges. V is a set of vertices and E is a set of edges. And V is divided into 2 types. It could be resources, it could be processes. Processes are represented as P1, P2 up to Pn, and resources are denoted as R1, R2 up to Rn. It depends on the number of types of resources that are available in the system. There are 2 kinds of edges, request edge and an assignment edge. Both are directed edges, and a request edge is Pi to Rj, where Pi is the process and Rj is the resource, whereas an assignment edge is a directed edge from Rj to Pi, where Rj is the resource and Pi is the process. So these are the components that are used in drawing the resource allocation graph. A process is denoted by a circle, the resources are denoted by rectangulars, and every instance of the resource is marked with a black small inner circle. And here you can see Pi is requesting for an instance of Rj, and that is denoted by a circle, process Pi, pointing to the resource Rj. And Pi is holding on to a resource, and that is a directed edge from the resource to the process. Now you can see this example of resource allocation graph. This resource allocation graph consists of 4 resources, R1, R2, R3, and R4, and there are 3 processes, P1, P2, P3. From this diagram or this graph, you can see that P1 is holding on to an instance of R3 and P1 is waiting for R1. While R1 is held by P2 and P2 is also holding an instance of R3 and still wants to make use of R2. Whereas process P3 is holding on to R2 and 3 instances of R4 are not yet utilized by any of the processes. So in this graph, we can see there are no cycles. Since there are 2 instances of the resource R3. If there were only 1 instance of R3, then this graph would end up in a cycle. So in this diagram, the resource allocation graph, you can see a graph. It has 4 processes and there are 2 resources, R1 and R2. And here you can see P1 is waiting for R1. And R1, both the instances of R1 are already occupied by P3 and P2. P3 in turn is waiting for the resource R2, which are both held by P1 and P4. So what is the importance of having cycles? This previous slide, which showed you as a diagram or a graph with cycles, does not show a deadlock condition because more than 1 instances of R1 and R2 are there. But when we look at this diagram, we can see a deadlocked condition where there are 3 processes, P1, P2, P3, and resources R1, R2, R3, and R4. And here you can see P3, P2 is holding on to an instance of R3 and still wants R2. R2 is already held by P3 and P3 in turn wants an instance of R3 which is not available, and this condition in turn goes to a deadlocked condition where one of the processes should release the resource that it holds on. Otherwise, this condition would indefinitely be the same because every process here, P1 is holding on to a resource and waiting for another resource, which is in turn held by P2. And P2 will not be able to complete it once it is holding on to 2 resources and still waiting for another resource, which is held by P3. And P3 cannot complete and release R2 because it still wants an instance of R3, which both are held by P1 and P2. Hence, this is a typical condition of a system with deadlock. And this can be easily seen by drawing a resource allocation graph. Not all cycles are deadlocked conditions. There are 2 cases. We've seen 2 types of resources. Sometimes the resources are having only 1 instance, and sometimes the resources are having multiple instances. When there are 1 instances, we have to be very, very careful that any cycle in the resource allocation graph can lead to a deadlocked condition. But in the case of a multi-instance resources that are available, then we have to check that if this current cycle is a deadlocked situation. So many times, cycles in a multi-resource graph need not be a deadlocked condition, whereas in a single instance resource allocation graph, having a cycle is a sufficient condition for a deadlock to happen. So some basic facts which I have now discussed. If this graph contains no cycles, definitely, and if this one instance or a single instance, then there is no deadlock. And if it contains a cycle, and if it's a multi-resource type of situation, then we have to check the possibility of deadlocks. So if there are no deadlocks, no problem. If there are no cycles, no deadlock. If there is a cycle, then we have to check if the resource is only just one instance or more than one instance, and then categorize accordingly. So let's take a look at some of the methods for handling deadlocks. There are times we can ensure that a system will never enter a deadlock state, or there are times we slowly allow a deadlock situation to occur and then detect and then recover from that situation of deadlock. There are times we also ignore the problem and pretend as if the deadlock has never happened. And then that's how many times system hangs, system crashes, and forcefully we restart. So that is what is deadlock management. So here we're going to clearly see these 4 important techniques of deadlock management. Number 1 is deadlock prevention, where we design a system that deadlocks never happen at all. Okay. Avoidance is a method or a set of techniques where we impose conditions for prevention, so that we do not allow the possibility of deadlock to just enter in. And every possibility of deadlock should be stopped using a deadlock avoidance algorithm. When it comes to deadlock detection, this is a technique where we allow the deadlock to happen and then check if the deadlock has happened, detect it, and if so, we will help to recover from that particular state of deadlock. And finally, the deadlock management is deadlock recovery. So let's assume a deadlock has happened. Then there is a need for recovery from a deadlock situation, which could even include termination of some of the deadlocked processes that are involved. So having seen some of the deadlock management techniques, let's take a look at the drawbacks of deadlocks. Whenever a system enters a deadlock state, there is a delay in the process initiation, and it is required that every process know what is their future need. So they are supposed to tell their future need so that we can able to identify whether a condition will enter a deadlock state or not. And in most cases, it is not possible. Practically speaking, a system or a process may not know what is its future need. And preemptions are more often needed. Quite often in a situation of deadlocks, we will use the concept of preemption. Then incremental resource requests are not allowed in this particular type of deadlocked conditions. So every request, every process must intimate before the start of execution, and not after it starts executing and later on in course of time incrementally give their resource requests. And of course, there are inherent preemption losses. So coming to the last slide, let's quickly summarize what we've learned in this video. We've seen that deadlock is a condition that occurs in operating system where a process enters a waiting state and remains in the waiting state because another process which is also in the waiting state is holding on to the resource that this process wants. A circular waiting condition is commonly happens in a system where there are more number of processes and one process waits for another resource which is held by another process which is next in the cycle. And that's how a circular wait condition happens. Deadlock occurrences can be detected, and deadlock occurrence is one deadlock management technique. We've seen 4 deadlock management techniques, namely deadlock prevention, deadlock avoidance, deadlock detection, and deadlock recovery. We've also seen there are 4 important, necessary, and sufficient conditions for deadlocks. That's mutual exclusion, circular wait, hold and wait, and no preemption. All these 4 conditions should simultaneously occur in order for a system to enter a deadlock state. And we've also seen that the resource allocation graph can be used for detecting deadlock in a system. If there are no cycles in a resource allocation graph, then we can rest assured that the deadlock has not occurred in the system and the system is in safe state. But if there is a cycle in the resource allocation graph, then we have to check if it's a single instance system. If the resources are only single instance, then a cycle is a sufficient condition for deadlock. And if there are multi-instances of the resources, then there could be a possibility of deadlock if there is a presence of a cycle in the resource allocation graph. So these are some of the references, and the commonly used textbooks. The popular textbooks are the Silberskopf, Tenenbaum's, and Williams-Talens. And there was also a web reference. Thank you all for watching. See you in the next video. Thank you.